All right, we're back. Now we've learned how to find the limit from a graph. We're going to figure out how to use algebra to solve limits. So we're going to consider this function here where f of x equals 1/2 times, and this is an absolute value here, negative 2x plus 4, close that, minus 4. Okay, here's the graph. So we can find the limit from the graph, right? So it says, what is the limit of the graph as x approaches 0? So if I come over here, x approaches 0 is right here. It's approaching negative 2 from the left and negative 2 from the right. So I know that that's negative 2. What about 2 from the right? So positive 2 from the right, it's approaching negative 4. And then the next one says as x approaches 10, and I can't see 10, but if it kept going, we could figure that out, right? I don't know why they showed us this graph and it doesn't approach it, but if it keeps going up, and let me get a piece of paper here. If it keeps going up, as x approaches 10, what's going to happen? It's happening at 10. What is the y value approaching, right? So we can imagine this is 6, 7, 8, 9, 10. It's something around here. So it's probably 4. So let's just put 4 for our estimate. We can't really tell. We'd have to get some graph paper and draw that out, but we'll leave it. Okay, so now we can actually use algebra to solve this. So this is saying what happens if I just plug in the value there. What happens if I plug in 0? So if I just find f of 0, right? I plug in 0 up here, it's going to be 1/2 times negative 2 times 0 plus 4, take away 4. That comes out to be 1/2 times the absolute value of 4 is 4. 4 times 1/2 is 2. 2 minus 4 is negative 2. Huh, they match. What about if I plug in 2? What's f of 2? 1/2 times, let's just do this part here, negative 2 times 2 is negative 4, plus 4, take away 4, this comes out to 0. 0 minus 4 means f of 2 is negative 4. Matches. Something tells me we'll know if this is right if this matches. What's f of 10? We have 1/2 times negative 2 times 10 comes out to be negative 20 plus 4 minus 4. So that negative 20 plus 4 is negative 16. Half of negative 16 is negative 8. Oh, half of this is negative 16 turns positive because of the absolute value. So half of positive 16 is 8. 8 minus 4, f of 10 is 4. That also matches. So what we've found out is that when a function is defined, that means there's a value at that point. So there is an f of 0, right? That exists. There is an f of 2. We can find it on the graph or by plugging it in at a point x equals a. Then what you can do is just evaluate the function at that point, right? So when you can plug in the value or find, you can just say f of a, and f of a will be equal to the limit as x approaches a of f of x. Okay, so in all of these points, when I evaluated the function at the value they gave me, it ended up being the limit as x approaches a. But you have to remember there's two constraints. The function has to be defined there and it has to be continuous, which this is defined at every point, it looks like from negative 2 at least until 10, and it's continuous. There's no holes or anything. Okay, so now we can use algebra to evaluate the functions. So let's move to these. So the first one says, what's the limit as x approaches 3 of 1/2 x squared minus 2x plus 3? So I have to think about what that function looks like. Is that function continuous? Yeah, it's just a polynomial function, right? It's not rational. There's nothing weird about it. So it's going to be continuous for all x's. The domain is all x's. So that means I can just plug in, I can find what the function's equal to when I plug in 3 for x. So if I solve that, and I'm always going to go fast through these algebra things, so if you have to pause it and work that out to get to make sure that what I'm writing matches what you would do, go ahead and do that. Because you end up with 4.5 minus 6 plus 3, which ends up being 1.5. So this thing, this limit as x approaches 3 is equal to 1.5 of this particular function. All right, so now let's look here. Here's a rational function. So it could be, is it continuous, right? We have to check that only at the point 3. So first let's check if there's a hole at 3. So what can x not be? Remember, the denominator cannot be 0. So if I come over here and check what that value would have to be, so x cannot be 3/2. That's the value that makes this thing 0. Luckily, we're not dealing with 3/2, we're dealing with 3, so the function is continuous there, so we can actually go ahead and evaluate it. So this ends up being 5 times 3 plus 2 over 2 times 3 minus 3, and that whole thing ends up being 17/3. So we can say the limit as x approaches 3 of this function is 17/3. Okay, here, another rational function. That one's quick and easy to look at. X plus 1, we know x cannot be -1. Luckily, they're not asking us to find -1. They're just asking us to find the value of the limit as you approach 2 from the left. So I can go ahead and plug that in. Let's evaluate square root of 2 plus 2 minus 1 over 2 plus 1 comes out to be 1/3. So the value of that is 1/3, right? Because this is square root of 4 minus 1. Okay, now let's throw some trig in there. Let's see if you remember that. So it's asking us to evaluate it at pi over 2. So you have to remember what the sine graph looks like. Is the sine graph continuous? Yes. So luckily we don't have to worry about it. There's no holes in the sine graph. So we're just going to go ahead and figure out what sine of 2 times pi over 2 is, which means what is sine of pi? Remember that unit circle? Sine value of at pi is equal to 0. So this limit is 0. If you don't remember that, I didn't bring my unit circle home today, but take that out and look at it. That's where you can get that value from. You're going to have to remember those or have that somewhere you can look at quickly. All right? So same thing here. What about if we have a cosine function? Cosine is continuous everywhere, so let's evaluate it at 2 pi over 3 over theta, so over 2 pi over 3. Okay, so here is that part where you should grab your unit circle or look it up. What is the value of cosine at 2 pi over 3? It's equal to -1/2 there. So -1/2 over, this is still 2 pi over 3. And remember, when I'm trying to figure that out, I can just multiply by the reciprocal. And then I know this cancels out. So the value of this function is -pi over 3. Oh, except, see here, live mistakes, just like it was real class. I forgot to flip the second one over. It's 3 over 2 pi. Hopefully you guys caught that. It's multiplied by reciprocal. The first time I just kept it the same, 2 pi over 3. Forgot to flip it. So in that case, nothing cancels out, and you end up with -3 over 4 pi. So this thing equals -3 over 4 pi. All right, and then what about logs? So here we can go ahead and just plug in. If you want to graph this, log base 8 of 11 minus x on your calculator, go ahead and do that. When I make these videos next time, I'm going to bring home a graphing calculator so we can graph it and see it. But it's continuous, so let's go ahead and evaluate that. Log base 8 of 11 minus 9. That's log base 8 of 2. And then how do we solve it from there? You guys remember those log rules? So 8, this means 8 to some mystery number equals 2. And to go from 8 to some mystery number, we have to cube root it, which is the same as saying x is equal to 1/3. So this equals 1/3. I'm going to write this there. So the value of this limit is 1/3. page. Let me see if that's centered. Okay, so now we're going to find limits at undefined values. So we have these three limits here. And what happens? So the reason we're calling these undefined, because if I evaluate this at -3, and I plug in -3, I get 9 plus -12 plus 3, which ends up coming out to 0. And the same for the denominator, it's also 0. Same thing here, if I plug in 1, I'd end up with 1 plus 4 plus 3, which ends up being 8. But then if I plug it in the denominator, 1 plus 2 minus 3 ends up being 0. It's also undefined. And this is the same function, just one's from the left, one's from the right, so you end up with 8 over 0. So these are all undefined. So what happens if that's there? Well, it doesn't necessarily mean that the limit is undefined. You still have to check it, right? So that's what this says right here. Just because a function is undefined at a value of x, it does not mean that a conclusion can be reached about the limit. You have to look at the function further. So from the graph of the function pictured to the right, what is the value of these limits, right? So here's the function. If I look at -3, come over here to -3, there is a hole, right? It's not continuous, but there's still a limit there, because what's the limit from the left? It's approaching what looks to be about a half, and from the right it's also approaching 1/2. So the limit there is 1/2. Okay? It just means there's not a value at -3, but the limit still exists. And then let's look at 1 from the left. This one says let's look at 1 from the left. So here is 1. From the left, the function's approaching -infinity. So if this is 1, from the left side, it's going down, so it's approaching -infinity, or you can say does not exist. And then 1 from the right, it's doing the opposite. It's rational function, right? It's going up, so it's +infinity, or does not exist. So while that you could have said it's undefined or does not exist for these two, it wasn't true for this one. You always have to do some extra checking. And sometimes you can even do some algebraic factoring to make it work. So how do you find those limits algebraically or analytically? So here are the things you can do. You can factor numerator and denominator, which is what we're going to do, to see if you can cancel out those discontinuities. And then if a factor is canceled out, the function has a discontinuity at that point, which we know from last year. Continuity at that point when the factor pair equals 0, right? And then let's say it doesn't cancel out. So if a factor does not cancel out, it's considered a non-removable discontinuity. And we will talk about that more. But you just need to know that if you're able to factor them out, it's what you call a removable. So this one is removable because you can factor it out, cancel out, or if you can't, it's a non-removable, okay? So let's practice with this same function here. So I'm looking at this, ax squared plus bx plus c, right? You should see that form here, ax squared plus bx plus c. So you got to think about how you can factor that out. Remembering what we did last year, this stuff's going to have to just come quickly to you guys. So I can see right now that I can factor out a 3 and a 1, and I have all positives. So it's going to be x plus 3, x plus 1. Okay, now let's look at the bottom. I'm going to be dealing with a 3 and a 1, but I have a negative here. But the middle term needs to be positive, so I know it's going to still be an x plus 3. This is x minus 1. So those two little expressions can be factored there. So now I can see, right, what I have a removable discontinuity. I can cancel these out. So I can remove that discontinuity at 3. So now I can find, this is going to be equivalent to whatever the limit of x plus 1 over x minus 1 is. And in that case, I can go ahead and plug in 3 because it works out. So let's plug in 3. If I do 3 plus 1 over 3 minus 1, I end up with 4 over 2. I messed up. It's negative 3. I was like, wait, why is my answer different? Because I forgot to carry through that negative. So it's negative 3 plus 1 over negative 3. Right here. It's x approaches negative 3, not positive 3. So negative 3 plus 1 is negative 2. And then negative 3 minus 1 is negative 4. Carryover errors, they matter, which ends up being 1/2, right? So I can say the limit as x approaches negative 3 of x squared plus 4x plus 3 over x squared plus 2x minus 3 is equal to 1/2, which is what we found when we looked at the graph, and this is how you do it algebraically. So it's just being able to do it both ways, because sometimes you may not have the graph. All right, one more set of notes, or page of notes. See if you can see that in there. Okay, so based on our knowledge from pre-calc, we know that if a rational function has a non-removable infinite discontinuity, that basically means there's a vertical asymptote there. So that's a vertical asymptote, right? That exists. Since the y values do not approach one specific value from both sides at a vertical asymptote, then the limit does not exist. However, we can determine if the one-sided limits approach negative infinity or positive infinity, like we talked about. In order to do this analytically, we will marry the numerical, graphical, and algebraic approaches. For each limit, determine the sign of the simplified function at the value to the right or the left of x equals 1. Okay, so for this example, it's asking you what is the value of this function when x approaches 1 from the left. So if we go back to the graph really quickly, we remembered 1 from the left is negative infinity. But let's say you don't have that graph. So how could you figure out what 1 from the left is? Well, you can pick any number to the left side of 1. So for this example, they just chose 0.9. So remember, we were able to get the simplified function when we canceled it out as x plus 1 over x minus 1. So when I plug in 0.9, I can tell that this number on the top is going to be positive, and this number on the bottom is going to be negative. Therefore, the whole thing is negative. Therefore, I can tell without having to actually evaluate it that the limit as x approaches 1 from the left of f of x, that function up there, is going to be negative infinity. So same, and then the same thing applies to the right. Pick a number to the right of 1. You end up with a positive over a positive. So therefore, this limit from the right side is positive infinity, right? Okay, so now let's look at this one. We're going to look at one with the square root in it. So we have this function g of x, which is the root of x plus 1, take away 2, all over x minus 3. So sometimes you have to rationalize a function to be able to factor things out so you can evaluate it. Because if we look at this, they're asking us to look at the limit as x approaches 3. So the function does not have a value at 3. If I plug in 3 in here, it's going to go undefined. But you can see from the graph that the limit exists because it's approaching the same number from the left and the right. So we're basically trying to figure out, what is this number here? Let's get exact, right? We can estimate from the graph, but if we do it algebraically, we can figure it out exactly. So remember, when you want to rationalize a function, you have to multiply by its conjugate. So this is a tool you can pull back out. So we're going to multiply the whole function by the conjugate of the numerator, which is still multiplying by 1. So when I multiply that out, I end up with the limit as x approaches 3 of, so when you multiply these pairs out, you end up with a root going away. So this ends up being x plus 1. And then this ends up being minus 4, negative 2 times 2, over When you multiply the bottom, let's just leave it like this for a second. Okay, so all I did was just say that that's what we have there. So now I'm going to simplify it. X plus 1 minus 4 is x minus 3. This is x minus 3 times root x plus 1 plus 2. And you can see how that was helpful because I can already see that I can cancel those out and make that 3 a removable discontinuity. So now I'm just dealing with the limit as x approaches 3 of 1 over square root of x plus 1 plus 2. Now I can just go ahead and plug 3 in and see what I get. So if I plug 3 in, I end up with this, which ends up being 1/4, right? So I know the value of this limit is 1/4. This would be kind of my final answer. And so I've gotten the exact value, which I didn't have to then estimate from a graph. So this is kind of fun because it's pulling all of those things you learned in Algebra 2 and pre-calc of simplifying a function as much as you can so you can evaluate it at a certain point to get the limit there. So more practice with that, and then we're going to deal with trig functions more, and then we're going to start blending all these different methods together. All right, see you next time. Bye.